Hello, today we will be doing homework 3, part C. We'll be using the Routh-Hurwitz criteria to find the maximum proportional controller gain in relation to our process gain for a series of 3 identical first-order systems under closed control. So to start out, from the last part of this homework, we derived this equation to relate the liquid level in the third tank to our set point using this transfer function right here, where GP is the transfer function of our entire process up here, this process here, GP. And so we had our transfer function of our measurement device, GM, which is usually just 1, so we're going to define that as 1. And we're going to define GC as KC, our controller gain. And then K is our system gain, as we know from the last problem. And then tau is our time constant. So if we plug these values into our H3 equation, we get H3 equals, we have K over tau S plus 1 cubed times KC over 1 plus K over tau S plus 1 cubed times KC, and then times GM, which is just 1, and then times our height set point. So to simplify this, we can multiply everything by tau S plus 1 cubed. And we will get H3 equals K times KC over tau S plus 1 cubed plus K times KC. And then we can expand out this term here. So we have tau S plus 1. Let's just start out by doing it squared. We get tau squared S squared plus 2 tau S plus 1, I believe. And then multiply it again by another tau S plus 1. We get tau cubed S cubed plus tau squared S squared. We'll get 3 of this tau squared S squared, and then we will get 3 tau S plus 1. I think that's what we get. And so now let's rewrite our whole expression here. So we have K times KC over K times KC plus tau cubed S cubed plus 3 tau squared S squared plus 3 tau S plus 1. All right, and now we can bring in the Routh-Hurwitz Routh-Hurwitz, if I'm spelling that right, criteria. Okay, I was close, but Routh-Hurwitz criteria. So the Routh-Hurwitz criteria will allow us to look at the coefficients of our terms here, and it will allow us to see if there will be any positive poles in our denominator here that would make this unstable. So how we're going to do this is we will kind of organize the coefficients of the terms we have in this equation in our denominator. So we will have our first, like the highest order, the coefficient of our highest ordered term, and then the second one, and then the third highest, fourth highest, fifth highest, and sixth highest. And then we will use those to solve for a B1, B2, B3, C1, C2, C3. So basically what this will allow us to see is we're going to look at the first column. We're going to look mainly at this column here, and if we have any signs that are switching, so if we have a negative and then a positive, or the amount of times that the signs switch between the values we have in this column would show us how many of those positive or right-handed poles that we have, which would show us where instability is occurring in our system. So in order to do this, we need to solve for B1 and C1. And how we're going to do this is we're going to basically solve in a diagonal, or like we're going to multiply our coefficients in diagonals. So B1 is going to equal our second highest coefficient times our third highest coefficient minus our first times our fourth. And then it's going to all be over that second one. So let's go ahead and fill in this table with our actual coefficients. So our highest order term here we have is s cubed. So the coefficient of that is tau cubed. So it will be tau cubed. And then the second highest order we have is s squared. So the coefficient of s squared is 3 tau squared. So that will be this spot in the table. And then our third highest is s, which is the coefficient of that is 3 tau. And then fourth is 1 plus kc times k. And then since we don't have any other terms here, our 5 and 6 are just going to be 0 because there's no other terms, there's no coefficients, it's just 0. So we can replace these into our B1 equation. So B1 will equal 3 tau squared times, I'll highlight this to make it easier to see, will be 3 tau squared times 3 tau, and it'll be, and then we will subtract this diagonal. So it'll be 3 tau squared times 3 tau minus tau cubed times 1 plus kck. and then it will all be over, good color, it will all be over this term right here. So 3 tau squared. So if we simplify this out a little bit, we will get 9 tau cubed minus, I'm not going to factor that out because I think it'll be simpler in a minute, over 3 tau squared. So we can factor out a tau squared. So we'll get B1 equals 9 tau minus tau KCK. So it'll be 8 tau minus tau K, so it'll be tau 8 minus KCK over 3. Right. So now that we have solved for B1, we can now solve for B2, and then once we solve for B2, we will use B2 to solve for C1. Okay, so to solve for B2, we will have to do the diagonals a different way because it's another column over. So for B2, we'll be using that outer column. It'll actually be our 5 times 2. So it'll be 5 times 2, whatever coefficients are in that position, and then minus 1 times 6. And both of the values in our 5 and 6 position are zeros, so it doesn't even matter what the denominator is. Our B2 equals 0. So now that we have that, we can solve for C1, which is the last value we'll need for our Routh-Hurwitz criteria. So our C1 is going to be 4 times B1 minus 4 times B1, 2 times B2, but our B2 is 0, so that will go to 0, and then over B1. So this goes to 0, and then for C1, we get what's in our 4 position is 1 plus KCK, and then that is multiplied by B1, but both of those cancel out. So we get C1 equals KCK, and we have B1 equals this expression up here. So now that we have these, we want to actually look and evaluate if everything we have in this column here, if there are any sign changes between these. So we can go ahead and write out what we have. So we have the first two right here. It's really thin. We have tau cubed, and we have 3 tau squared. And tau is our time constant, which is a non-negative number. It's always going to be positive. So this is positive. Again, this is positive. It's squared. It's times 3, a positive number. This is also positive. And then we have our B1 value. So we have tau times 8 minus kck over 3. And we have our C1, which is 1 plus kck. So we want to evaluate our B1 and C1 and see what values make these terms positive, because we want to avoid any sign changes, so we want to make sure they're not negative. So we can evaluate them. So tau 8 minus kck over 3, we want this whole term to be greater than 0. We can multiply everything by 3 and divide by tau. So we can get 8 minus kck to be greater than 0. And then we want to just solve for our, I believe, just our kc value. So if we add, or if we add it to the other side there, we can get a is greater than kck and then divide by k, so 8 over k must be greater than kc. And then similarly, for the other one, we have 1 plus kck. You want that to be greater than 0. So if we subtract 1, kck must be greater than -1, kc must be greater than -1 over k. So we have these bounds right here, and now we can move on to Colab and plot this out. All right, so I went ahead and just put in a few values. I set k to 1 and then kc to 8 over k, like we found in we found that to be a boundary through the Routh-Hurwitz criteria. And then I've set tau to just 1.5. And so now we need to define the other transfer functions that we have. So we had gm for the transfer function of our measurement device, which we just set that as 1. We have gc, which we just want that to be kc. And then we also have gp, which is equal to our overall transfer function from our process, which is k divided by tau times s plus 1, and then that is cubed. I think that's all we have. And then we need to create a variable for our entire function, or our entire transfer function. We're just going to call it gclosed because it is a closed loop. So this is our whole thing that we had earlier. Let me find this. So it's our GP GC over 1 plus GP GC GM. So we can go ahead and type that. So it is GP times GC, and then divided by 1 plus GP times GC times GM. Right. So now to simulate this, we can do simulate our G closed, just give it a variable, and we need to give it domain for this time. We'll just set that to 1 right now, and that will give us a return of our time and our heights. Okay. Yeah, so there's not supposed to be a comma there. And then we can just plot this out. So fig equals make underscore subplots, and then fig dot add underscore scatter, and then we want our x to be time, our y to be our height, and then mode to just equal lines. I think that's all we should need, and then we should be good to just plot. All right, so this is what we get when we have just these values in here. And it looks like we want to see more time and time steps to get a better idea. Yeah. So we can see that at this value, this is exactly at our boundary for our controller gain that we found. So as we can see, there's steady oscillations. It's not diverging really. So let's see what happens when we change this to a value just below and just above the boundaries that we found. So we can just start by making it just above, or let's do just below what we had first. Okay, so this is still within our boundary of a stable system through our Routh-Hurwitz criteria, and we can see that it's converging, so the system is definitely stable because again, Kc must be, let me find it on my iPad here, Kc must be less than 8/k. So we are still within the boundary, we're more within the boundary now. So if we actually turn this into a plus, if we go outside this boundary, what we will expect to see is that the system will become unstable. The oscillations will probably be diverging instead of converging like this. Yeah, so as we can see here, just outside the boundary, just 0.1 outside of this boundary here, these boundaries of our controller gain value here, it is unstable. So I believe that's all we had here. Yep. So thank you for watching.